we want to talk about some approximate methods for solving differential equations, and we want to look at asymptotic methods for approximating solutions to the differential equation at hand. So let's describe what the basic idea of an asymptotic expansion is. We are presented with a problem with a small parameter. Typically the small parameter is given in terms of a non-dimensional parameter called epsilon here, which is much less than 1. And we want to then express the solution in terms of a correction or a perturbation expansion when epsilon is 0, and then successively correct for the fact that epsilon is actually not equal to 0. So we're going to be looking at an example from spring mass damper system, and so we will see that there are two kinds of perturbation expansions that arise: a regular perturbation expansion and a singular perturbation expansion. Concretely speaking, in terms of the spring mass damper system, if you think about the problem with small damping, so a mass spring system with a small amount of damping will oscillate and slowly damp. And so that slow damping would be a small correction or a regular perturbation. We can alternatively think also about a spring mass damper system with small mass or small inertia, in which case this will be a highly damped system which will oscillate when the mass is not equal to 0. And so this will turn out to be a singular perturbation problem. A singular perturbation because mass shows up as the multiplier of the highest derivative term, and that causes this perturbation expansion to be a very different singular. So let's cast the problem in terms of the mathematical model here. We have mu double dot plus cu dot plus k u equal to 0, mass, dashpot or damper, and spring constant here. And the initial conditions are that the displacement is given and the initial velocity is equal to 0. And so as we have stressed before, we want to first cast the problem in its natural setting in terms of a natural non-dimensionalization. We want to scale the problem, so we want to make the displacements non-dimensional with respect to the initial displacement, and that's a natural length scale, natural scale for displacement u0. We divide by u0 and define a v. And so the question then is, how do we make time non-dimensional? And what is a natural time scale to make time non-dimensional, t over capital T? And so we can discover that by substituting t, capital T, into the problem. We rescale time, and so the rate of change with respect to the original time is rate of change with respect to the scale time tau times d tau dt, and d tau dt, of course, by definition is 1 over t. And so we're going to substitute this in the problem and discover what would be natural for capital T. Of course, from the physics of the problem, you already know that there is an oscillation time scale in the problem, t sub 0 or t sub oscillation, to, which we can express in terms of mass and spring constants, square root of m over k. And there is a different time scale, which is a decay time scale, which we can estimate also in terms of the damper constant c and in terms of the spring constant k from the equation. So we have these two different time scales, which are physical time scales. They represent different physical processes, and there is a multiplicity of them present in the problem. And so if these two time scales are widely separated, then in fact it's a problem with multiple time scales, and that would be a very natural thing to express in the solution method. So this is going to come up as we talk about this further. So now if we think about a problem with small damping, a spring mass system with small damping, here's the equation which we have non-dimensionalized. We have introduced the non-dimensional variable, so u0 multiplies v because of the scaling, and the time has been converted to tau here, so we get 1 over t square for the second time derivative and 1 over capital T for the first derivative here. And so then if we want a problem with small damping, which would mean that the inertia term and the spring force are essentially going to be in balance, in approximate balance with each other, a damping playing a small role. So this term is going to be relatively small compared to these two. So equating the order of magnitude of these two terms, setting this coefficient and that coefficient in the brackets equal, allows us to estimate the time scale of oscillation, capital T equals square root of k, square root m over k. And so we're going to make this choice and use it in the following development. Of course, at this stage, we can also evaluate the importance of the damping term. So if we take this coefficient, which is sitting in front of the damping term, and divide it by this coefficient, which is what we're going to get when we have the non-dimensional equation. So the numerator is this coefficient here, denominator is the coefficient of the inertia term, and we just clean it up, and we will see that it is the ratio of c with square root of m times k. And so we're going to call this a new symbol defined as gamma. This is a non-dimensional constant, and its value will determine whether the damping is small or not. So when gamma is very small, we have small damping. The equation in non-dimensional terms can be recast in this way. There is a single coefficient gamma, and it's going to be convenient later to speak in terms of gamma over 2 sort of naturally appears in the problem. So we redefine gamma in terms of beta. So beta, 2 times beta is equal to gamma. And so in the original variables, beta is defined in this way, c over 2 times square root of m times k, and it's this parameter which is small. So this is the quantity which is going to play the role of epsilon that we mentioned before. And so here is the differential equation presented in a cleaned up form. Second derivative, 2 times beta, beta is the small parameter, dv d tau, plus v equal to 0. And so this damping term, which is small, initial conditions, the initial displacement is 1, and the initial velocity is equal to 0. And it's this problem that we want to solve. We want to illustrate an asymptotic expansion method for solving this problem. And much of what we are doing here can be applied to more general problems. Can be applied to nonlinear problems, can be applied to higher order equations, and so on. So it's a powerful technique. And so the way we will proceed is that we will say that at leading order, the solution is without damping, and then we perturb the solution without damping, and thereby correct that solution. So that is the physical idea that we want to mathematically exploit in terms of how the small parameter enters the problem.